Hello and welcome to session 2 of the 7th massively open online course for the University of Nicosia with a master's degree in digital currencies. This is Andreas Antonopoulos. Let's see. In today's session, we're going to talk about the Byzantine generals problem, achieving consensus in an untrusted environment and how Bitcoin does it. And we'll talk specifically about the consensus algorithm in Bitcoin. Don't forget, as we're having this conversation, please submit your questions on the YouTube channel, and George will be curating them and providing them back to me here. In the meantime, we have some questions from the forums we'll address right away. Melissa asks, why does Bitcoin's difficulty adjust every 2016 and not every 2048 blocks? Thanks. If you didn't notice, 2048 is a power of 2, and 2016, which is the actual difficulty retargeting interval, is not a power of 2. And so why is that? Well, the simple answer is that Bitcoin's clock runs on a 10-minute heartbeat. There are 144 10-minute intervals in one day, and there are 1,008 10-minute intervals in 1 week, and 2016 10-minute intervals in 2 weeks. So difficulty adjustment in Bitcoin is designed to operate every 2 weeks, and in 2 weeks, 2016 blocks have elapsed. Try it yourself at home. 144 times 7 times 2, and you'll get the 2-week interval of 2016. Jope asks, how does the network know which chain to follow if there are 2 blocks that are discovered at more or less the same time? What happens then? Well, what you're describing, Jope, is a situation that happens approximately once a day, and this is known as a fork. This is a normal part of the operation of the network. So what happens when there is a fork in the chain? If 2 blocks are discovered more or less at the same time, both of those blocks are valid, both have sufficient proof of work, both are better than the difficulty target. They have a higher level of difficulty than the difficulty target, and both are broadcast almost simultaneously. What will happen then is nodes around the network will take the block that they hear first. So imagine the network is spread out across the world with various interconnected systems. Now, they're not interconnected based on geographic proximity. They're interconnected in a mesh network based on random selection of nodes. And so how a block propagates has to do a bit with how the connectivity of the network is, but it also has to do with latency, the time it takes to transmit across the communication networks. So assume that the 2 blocks are transmitted at the same time, and assume that they start from 2 different parts of the network, and then they spread out and propagate across the network. Part of the network is going to hear the block on this side first, and then it's going to hear this block a few seconds later. And what that part of the network is going to do is it's going to take this block as the winner, the one that propagated first to that side of the network. And when it hears the other block coming a few seconds later, it's going to discard it. It didn't get there fast enough. Meanwhile, on the other side of the network, this block will be heard first. This one will be heard second. This one will be selected as the winner. Now, essentially, the network is now split into 2 opinions as to which is the longest chain, which is the highest difficulty chain. One has block A at the top, and the other one has block B at the top. If miners are equally distributed between the 2 parts of the network, for simplicity, let's assume that's the case, then they will immediately start building a new block on top of what they think is the longest chain. So on this side, they're going to be building a new block on top of A, And on this side, they're going to start building a new block to extend the chain that ends with B. In every block, you have to specify who the parent is, who the previous block is. And so half the network is going to be specifying block A as the previous block. Half the network is going to be specifying block B. As they continue to mine, presumably, somewhere someone is going to find a solution. If the solution is built on top of block A, then that chain becomes longer. The other chain is no longer the longest chain. And all of the nodes that had previously selected the block B chain will discard it, because they'll now see an alternative chain that has A and maybe C, the new block, that is longer than the chain they have, which has B. So they will discard that chain, essentially orphaning the B block, even though it won from their perspective, because the other side extended the other chain faster, then they will discard it. So essentially, forks are resolved by waiting one more block and seeing which one gets the new block. Now, there is, of course, a very small possibility that, again, two blocks will be discovered almost simultaneously, extending the two chains, in which case you will have a two-block fork, and then the process repeats. We wait one more block to resolve it, to see which one gets a new result. One-block forks happen about once a day. Two-block forks are much more rare, and should really not happen if the network is well connected. And of course, if you see more than two blocks, something else is going on. Olubisi asks, how is hash power really measured? Well, Olubisi, if you look at the result of hashing a block, and if someone presents a valid block, that block has a header and a hash. The hash of that block starts with many, many, many zeros. And we know it's smaller than the difficulty target. So it should have a prefix of several bits of zeros. Now, based on how many zeros are in the front of the block, you can estimate on average what the probability of finding a block with that many zeros is, what the probability of finding a hash, sorry, with that many zeros in the beginning of it is. And therefore, you can calculate on average how many hashes it took before such a block was discovered. So let's say if the probability of finding such a block is 1 in 50 quadrillion, then on average, you would assume that it takes 50 quadrillion hashes to discover such a block. And that is the measure of the hash power. It is how much, on average, it would take to find a block of the current level of difficulty. One useful example, which will help clarify exactly what the role of randomness, what the role of the difficulty target, and how we identify the probability, we'll look at when I answer the next question, which clarifies this a bit more by discussing how we would do this with, for example, dice. Uta Bayer asks, in our notes on page 20, step 3, the hash is reviewed against the desired pattern. In the case of Bitcoin, how many leading zeros it has, an outcome that is effectively random. If the hash matches the pattern, the miner has a valid block and will win an economic prize. Uta asks, how is the hash reviewed against the desired pattern? How is the desired pattern defined? Especially since the nonce itself is a random number. So what the miners are doing is they are committing to a specific block that they've constructed, what we call a candidate block. They've constructed this block with new transactions that have so far not been confirmed. And they calculate all of the parameters of the block to construct a block header. And then using a nonce, they try again and again and again to hash that block header with a nonce to produce the block hash. And what they're looking for is for the block hash that is produced to be less than a specific target. So in terms of numbers, if you think of the hash as a number, it's a number. Whether it's represented in hexadecimal or decimal or binary, it's a number. If you think of the block hash as a number, the fact that it has lots of zeros in the beginning means that it is a smaller number. It's smaller than if it didn't have lots of zeros in the beginning. So as a result, what we're looking for is for the block hash number to be less than, smaller than, the number that represents the difficulty target, which again is a number that has a few zeros in front of it. Now, how is the difficulty target calculated? That's a process that happens every 2 weeks, and it is calculated by adjusting the previous difficulty target by a certain percentage or proportion. If the previous difficulty target was making blocks come out of the network, let's say 10% too fast, so instead of every 10 minutes, the average block time was 9 minutes, then the network is running 10% too fast. Let's say the difficulty then, at that moment in time, is 250, just to pick a number. Okay, now we need to adjust that to make it 10% more difficult. So the number would be decreased to 225, reducing it by 10%. And if previously finding blocks that were had a fingerprint, a hash less than 250 was difficult, finding blocks that have a fingerprint less than 225 is more difficult by 10%. So as a result, that's how the difficulty is retargeted. Let's look at this example on a much smaller basis, much simpler basis, and look at it with dice. Let's say you have a game of chance where players are sitting in a room together, and they each have 2 dice in their hands. And what they're trying to do is roll less than a specific number. Now, in the case of the dice game, the difficulty can be defined as any number between 2 and 12. So the lowest difficulty you can, so the highest difficulty and the lowest number you can throw is 2, because you have 2 dice. So if you throw both of the dice showing 1, then their sum is 2. That's the smallest number you can throw. And the highest number you can throw is 12. So essentially, we set the difficulty to be between 2 and 12. Let's say, for example, we set the difficulty to 8. Now, the players start throwing rounds of dice. And they can throw dice as fast as they possibly can. And what we're waiting for is for one of the players to announce that they have thrown dice less than 8, summing up less than 8. So maybe a 4 and a 3, or a 3 and a 3, or a 3 and a 2, or a 2 and a 2, or a 3 and a 1, whatever. Some combination where the sum is less than 8. Once they do that, they announce it, they say, I have it, and they win that round, and then we try again. Now let's assume that we're trying to measure the time it takes, and we notice that we want to find a winner every 10 minutes, and we're finding winners, let's say, much more often. Let's say we're finding winners every 5 minutes, twice as fast as what we want. Okay, so in that case, by reducing the target from 8 to 4, we're making it twice as difficult to find dice throws that are below that target. So everybody says, okay, let's recalculate the difficulty. Everybody counts how many minutes it took for this last 2,000 rounds, and then proportionally adjust the difficulty. Everybody comes up with the same conclusion. The new difficulty should be 4 to make it twice as hard. Everybody agrees to that. They don't even need to talk to each other. They know that 4 is the answer, and they start throwing dice again. After a few minutes, after 10 minutes, hopefully, someone goes, I have it, and they have a 2 and a 1, and that adds up to 3. Less than 4, great, they win. Everybody is expecting them to throw something less than 4, and everybody knows that should be the target. All done the same calculation. If they or 5 and say, I won, everybody else says, no, you didn't win. According to my calculations, the target is 4, so you didn't win with a 5. You have to throw a 3 or below. So that process repeats. Essentially, therefore, in the case of Bitcoin, the hash of a block, which is influenced by a nonce, and because you use a nonce, the hash that you produce is random, just like throwing dice. Just because it's random doesn't mean that you can't measure it. It's measurable. You can measure that hash. That hash is a number. You then compare it. You say, if the hash you have is less than the difficulty target, which is another big number, then you win, and you announce your block to the world. If it's not, you throw the hash again. You try again, change the nonce, try a new hash, and you do that. I hope that answers the question of how the hash is reviewed against the desired pattern. They're both numbers. How is the desired pattern defined? It's a number. It has been adjusted every 2 weeks since the beginning of Bitcoin. It started set at a fixed rate, which was pretty high, meaning it was very easy to mine. And since then, as more and more people have participated in mining with more and more powerful equipment, the desired pattern for Bitcoin, the number that is the difficulty target, has decreased and decreased and decreased, making it more and more and more difficult to find a solution. Uta asks, why is Bitcoin the best solution to date? There are other blockchain systems designed to address some of Bitcoin's flaws, flaws within quotation marks. For example, using less expensive consensus methods, providing better scalability and smart contract functionality. Well, Uta, really, the issue here is that best is not easy to define in this particular situation. Best is really a matter of fitness, and I like to use terms from evolution to describe currencies, digital currencies, because they operate in an environment of competition for resources, as well as fitness to a particular application. So really the question is Bitcoin the currency or system that is most fit or best fit to serve certain applications? And that really depends on what the applications are. Smart contract functionality, not very much. Smart contract functionality is better served by more flexible systems. Bitcoin can do smart contracts, but not the most flexible of smart contracts, so it's more difficult to do them. However, that represents a trade-off, and that trade-off is security. So in order to do much more robust security, Bitcoin has restricted smart contract functionality. And Bitcoin smart contracts, the scripts within Bitcoin, have never been hacked. By comparison, some of the other platforms that have chosen to use more flexible smart contract functionality, recently we've discovered perhaps some bugs that when the smart contract functionality isn't implemented correctly, can lead to compromising the smart contract. That's not a coincidence. That's not something that just happened. It's something that happened specifically because of the much greater complexity and flexibility of the smart contract language in that case. And so Bitcoin is making an explicit trade-off. Less flexibility in smart contracts, more security. And that trade-off is also happening in the consensus mechanism. The consensus mechanism is expensive. And the reason for that is because Bitcoin is, again, making a trade-off, a design trade-off that says more strong immutability, more decentralization, more protection against external attacks, much more difficult to change the blockchain. The consensus mechanism that uses energy as a foundation for both value and security. And you can do a less expensive consensus mechanism but it's arguable that it is not as secure, not as resistant to attacks, not as immutable as Bitcoin's blockchain. And then the question becomes, do you need that level of security for any particular application? And to that, really, the answer is it depends, and it depends on the application. So we really should be thinking about these systems in terms of whether they are a best fit for a specific application, rather than whether they are best as if they are playing in a competition where all things are equal. They are not. Okay. Macy, try pronouncing that name. I can't pronounce the last name either. Macy asks, is it practically possible to experience a split brain scenario in the Bitcoin network? I will describe this hypothetical scenario. For technical reasons, the network is suddenly cut in half for a considerable period of time. Both parts of the network do not have any effective means to communicate with each other. After a certain period of time, communication resumes. How would both networks reconcile their ledger state? And the reason Massey is proposing this hypothetical is, what would be the practical implications of, hypothetically, the Chinese internet and the miners who are part of the Chinese internet are cut off from the rest of the network because of deliberate updates in the Great Firewall of China? What would be the implications for the hash rate, consensus, and block difficulty? So let's look at this from two different perspectives. First of all, is it practically possible to scenario in Bitcoin? Yes, of course it is. On the other hand, however, it is very unlikely that such a split would be even. It's more likely that a small portion of the network is disconnected for a short period of time. It is also not likely that such a split would last a considerable period of time. There are many, many ways to communicate information, and Bitcoin is really simply information. And therefore, any communication network between two nodes could be used to reconnect the network and stitch it together. And there would certainly be a lot of incentives. If the part of the internet was shut off, people could use private lines or network lines. They could use a modem to dial up another location and transmit information over a modem or several modems. They could use shortwave radio. They could use a number of different technologies to reestablish communication. But in a very practical sense, if there are significant changes that cut off a significant portion of the network, especially cut off the miners who are mostly located in China, at least 60 to 75%, I would guess, are located in China, then that would have some significant implications. It would not be able to happen because of updates in the Great Firewall of China, because no matter what updates happen, people can devise ways to get around that. It would happen only if really the whole of China was cut off from communications from the rest of the world. And that's a scenario where more than Bitcoin would be impacted. But if you take that scenario, then miners in China would not have access to transactions generated elsewhere. And that would significantly reduce the number of transactions they could mine. Meantime, the mining hash rate for the rest of the network would decline. There would not be enough miners in the rest of the world. And so what would happen effectively is a fork of the network. There would be a blockchain fork. A minority of miners in the rest of the network would continue to mine. They would produce blocks. Those blocks would only be seen by the rest of the world. Chinese miners would continue to mine. Those blocks would only be seen by the Chinese internet if it was still running. And transactions would either be on one or on the other, because presumably transactions can't get through either. If this persisted for longer than 2 weeks, you'd have a difficulty retarget in that time. Both chains would retarget, and they'd retarget in such a way as to reset the block issuance rate to approximately 10 minutes. If you had, for example, only 25% of the mining capacity left in the rest of the world, then after 2 weeks, the difficulty would be reduced by a factor of 4, which is the maximum retargeting that is allowed. And the rest of the world would start mining 10-minute blocks again, and would continue with that chain. Similarly, on the Chinese side, there would be a retargeting, and that side of the network would start remining at 10 minutes. But of course, there would be an imbalance in the transactions. This is a really, really bad scenario, but the moment something like that happened, there would be many, many people working to reconnect the two sides. And it's really kind of an extreme hypothetical. Okay, let's see. The next question. Jesse asks, what happens when all the Bitcoins are mined? The miners would no longer be mining coins, so how do the transactions get verified? All right, this is a really important thing to understand. It's one of the main misunderstandings of mining, and it's a very common question I get. The purpose of mining is not to generate new Bitcoin. Okay, let me repeat that. The purpose of mining is not to generate new Bitcoin. The purpose of mining is to validate transactions and secure the network. The generation of new Bitcoin is one part of the reward mechanism. It's a side effect, and it's one part of the reward mechanism that miners get. The other part of the reward mechanism is transaction fees. So today, every block generates 12.5 Bitcoin in reward, and approximately 1/10 of a Bitcoin in total fees across more than 1,000 transactions. So if you add that up, that's 12.6 Bitcoin. More importantly, let's look at the ratio. At the moment, that means that the ratio between reward and fees that a miner earns is 125 to 1. 125 to 1. So for every 1 unit of fees, the miner gets 125 more in new coin reward, which means that miners are currently heavily biased towards seeking the reward from the blocks, and they don't care about the fees too much because they only represent 125th of their reward. Now, over time, the reward from new coins decreases, and presumably as the network gets used more, the reward from fees increases. Let's roll to the end of the period and look at how it looks then. The year 2141 is the theoretical endpoint. That's the year when the last Satoshi is mined. Now let's assume that at that point, a block has 1 Satoshi reward. That's the minimum reward. And let's assume that at that point, the block has 10,000 transactions in it. What's the minimum fee that can be paid in a transaction? So let's say all of them pay the absolute minimum fee that can be expressed in Bitcoin. Again, that's 1 Satoshi. So 10,000 transactions, each paying 1 Satoshi, that's 10,000 Satoshis in fees. The block reward itself is 1 Satoshi. So now, as you can see, the ratio of reward has shifted quite dramatically. And it's 1 over 10,000, or 10,000 to 1 in favor of fees. So the fees are worth 10,000 times more than the block reward for miners at the end of the period, even before the block reward goes to 0. If you think about it, essentially the network has gradually transitioned over a very long period of time from a focus on new coins with a bias of 125 to 1 to a focus on fees the opposite way with a bias of 10,000 to 1. At some point, there's a crossover as reward goes down and fees come up. And that crossover point, at some point, will be maybe 1 to 1. So we can imagine a point where maybe the reward is a quarter of a Bitcoin for new coins, and the total fees are a quarter of a Bitcoin. At that point, a few decades from now, maybe, or less, then the reward that miners are seeking is half from new coins, half from fees. The fees are now 50% of their focus. And so they start focusing on fees much more heavily. By the end of this period, when all the Bitcoins are mined, the miners have been focusing on fees for decades. And they simply continue mining, and they continue mining for the fees and not for the new coins. Yuri's asks, depending on which source I read, China contains somewhere in the order of 70 to 80% of all Bitcoin mining hashing power. Would this not make Bitcoin highly susceptible to a 51% attack in the event the Chinese government, for whatever theoretical reason, decided that the failure of the Bitcoin ecosystem was in their interest? For example, physically seizing larger miners and therein their hashing power, and/or preventing smaller miners from operating through legislation and prosecution, and therefore magnifying the influence of the larger miners seized. Does the Bitcoin network have any resistance to such a play of events? Let's take this one at a time. Yes, China has 70 to 80% of all Bitcoin mining hashing power. However, it's important to realize that this is not all in one place. China is a very, very large country. And the mining power is distributed among many different mining farms, possibly dozens, hundreds, thousands even, that are spread out throughout the country in various locations, connected to different forms of power, hydroelectric, coal-fired plants, and many other forms of energy. So even though theoretically the Chinese government could decide the failure of the Bitcoin system was in their interest, and theoretically they could seize large miners and their hashing power and try to prevent smaller miners from operating through legislation and prosecution, practically this is a very, very large operation that would require a lot of manpower and a lot of focus and effort. Keep in mind that in many places where mining occurs, the mining income represents a significant portion of the income of a particular town or province or municipality. And so imagine in that province that you have a hydroelectric power or a coal-fired electric plant that is producing excess electricity that cannot be sold because there's really not enough distribution network to transmit it anywhere. And that electricity is being wasted. And one day, a business person comes in and says, we're going to use that old abandoned building and we're going to pay you hundreds of thousands of dollars a month for the electricity that you're not currently using. That kind of influx of money in an area will influence a lot of officials, meaning that that kind of money can buy every police officer, every judge, every official, every government representative up and down the chain. So one of the issues here is that when people are making a very significant amount of their income from these mining farms that have injected a lot of money into rural areas, and the Chinese government says, we demand that you shut down the mining farm, the likely answer is, what mining farm? We don't have any mining farms here. And even if enforcement happened, yeah, sure, we shut it down. It was shut down yesterday. It's back on today, but nobody noticed. It's very difficult to actually shut down and prosecute every mining farm when it's not clear where they are, who runs them, and under what conditions they're running. But theoretically, of course, a concerted effort by the Chinese government, they could do this. And if they did that, what would happen is that we would see initially a reduction in the hashing power, and then a concentrated 51% attack. In that case, it is highly likely that that the rest of the world would implement the opposite of a Great Firewall of China and try to isolate the attack vector, try to isolate the Chinese mining farms from participating in mining by disconnecting them from mining pools, and disconnecting the nodes that have Chinese IP addresses or going through the Chinese internet in order to contain that type of attack, which would also make it much more profitable to mine elsewhere. So I think the network would survive this. Another possibility would be to make small changes in the protocol, or even big changes in the protocol, to, for example, change the hashing algorithm in order to deal with a significant, sustained, systemic, and existential attack on Bitcoin. But hopefully that will not happen. The incentives and profits from doing mining are such that even at a government level, the flexibility and possibilities created by digital currencies such as Bitcoin, for strategic reasons and political reasons, are quite interesting. Jerome asks, how will the transaction fees increase? Bigger blocks or bigger fee per transaction? I think this refers back to my description of how, over time, there would be more reliance on fees instead of new coins mined. Keep in mind, this is over a period of more than 100 years. And so the answer really is that the fees would increase because we have more transactions. And more transactions at that point means bigger blocks or some other optimization, but more capacity, effectively. And more capacity may come in the form of bigger blocks, will probably come in the form of bigger blocks and several other optimizations to improve the capacity or increase the capacity of the Bitcoin network. A 10 times increase in the capacity of the Bitcoin network, or a 100-time increase in the capacity of the Bitcoin network, is something that, based on the dynamics of computer science and all of the other places we see Moore's law have an effect, is not even a fanciful or strange idea. It's quite clear that Bitcoin's capacity will be increased by several orders of magnitude in order to provide capacity for more and more use of the system. So it's just a matter of when, how, and in what sequence the capacity is optimized. But we're talking about a period of time of 130 years from now, until the last Satoshi is mined, and certainly several decades until the mining reward becomes very, very small. So the answer is transactional fees will increase because there will be more transactions, more adoption, more users, and therefore more fees, not because the fees are higher on every transaction. OLBC asks, considering that the network produces one successful block every 10 minutes or so, what would happen if there are too many transactions announced at once? What happens to subsequent transactions, which are dependent on the positions of earlier transactions? Let's take that in two parts. First of all, what would happen if there are too many transactions announced at once? They're queued. There is a queuing mechanism called the memory pool, or mempool, or the transaction pool. And so you can actually go to various sites. George, if you could pull a mempool link up for our audience, that would be great. And what the mempool is basically the temporary storage of transactions that have not yet been confirmed. When a transaction is transmitted on the network, every node stores it temporarily in memory in the mempool while it's propagating. Mining nodes keep a mempool. The mempool is consistent, relatively consistent to 90–95% across all of the nodes over some period of time. Eventual consistency. And the mempool contains all of these transactions. In normal operation, the mempool contains a few hundred transactions to a couple thousand transactions, which means that it contains 1 to 2 blocks worth of transactions. And as transactions are confirmed and included in blocks, they're removed and cleared from the mempool, and the mempool decreases in size. If a lot of transactions are announced at once, you'll see the mempool suddenly increase in size. Maybe it's got 3 or 4 blocks or 5 blocks or sometimes even 10 blocks worth of transactions. And then these transactions sit in the mempool. They are prioritized by the miner based on a selection algorithm that is based on the miner's incentives to maximize their profit. In this algorithm, they choose transactions from the mempool in order to maximize the profit in fees per kilobyte for each transaction. And they will take into consideration transactions that are dependent on other transactions also in the mempool. We call these chained transactions. So they take into consideration various strategies, including a strategy called child pays for parent, where one transaction and its dependent transaction may have a total fee that's really, really good, but it's all carried in only one of the transactions. So they do consider them as a whole for prioritization. So miners pick transactions. They prioritize based on their own profit incentive, and they include them in blocks to maximize the profitability of their blocks. As they choose them, they get cleared from the mempool, the backlog decreases, and in the next block, more transactions are included and more transactions, and eventually, after 8, 9, 10 blocks, the backlog is cleared. This is something that happens on a regular basis. Every few weeks, sometimes for several days, you'll have a very large number of transactions in the network. And in that case, what happens is the average fee that is paid for a transaction tends to increase as people notice that there is congestion and that the probability of their transaction being included in the next block is lower if they don't put sufficient fee. They increase the amount of fee in order to get prioritized in the next block. And some people decide, I don't need to increase the fee. Let's say I'm moving money from a paper wallet offline storage to a hardware wallet, and I'm not going to touch it for 2 weeks. I don't care if it's in the next block. I don't care if it's in the next 3 blocks or the next 10 blocks. As long as it gets confirmed in, I don't know, a day, I'm good. So I'm going to put a fee that's going to get it confirmed in 10 or 20 blocks. And that will be enough. Somebody else is doing a transaction where they need faster confirmation. Let's say you're selling a car and you want to make sure that you receive the payment, wait for 2 or 3 confirmations before you physically hand the other person the keys to the car. I sold my car for 3 confirmations. After 3 confirmations, I handed the keys to the buyer. Now, it would be very inconvenient if it took 10 blocks for that to happen. We had to wait an hour and a half for the confirmation of that transaction. So in that case, if I'm making a transaction for, I don't know, $10,000, quite honestly, putting $1 in fees or even $2 in fees to make sure it gets confirmed in the next block is not really a significant expenditure. Olubisi asks, given two computers on the network with massively different computing power, is there a definite advantage to the one with greater computing powers? Because guessing a correct nonce is based on random luck. The computer with greater computing power has more potential to be luckier, because within the same length of time, it would have put in more guesses. But the one with the lesser computing power may also be lucky in its guess. Is this correct? Yes, it is correct. The probabilities we're talking about are in the order of quadrillions of calculations per second. So you're probably better off playing your state lottery than expecting, or a scratch-off card, than running a miner and hoping that you're going to find a valid block with a fraction of the computing power that would be required. So yes, if you have a very small amount of hashing power, and the probability says that you should only find one block a year, you might find one today, and then you might find one tomorrow, and then you might not find one for 3 years. That's how probability works. And if you found one today and one tomorrow, you would have been extremely lucky. But then you're going to be using electricity for 3 years, maybe without finding any. Or you might not find any for years. So it works both ways. Really, that's one of the reasons why smaller systems participate in a pool where they share their luck with everybody else, so they can get a more smooth probability of returns. So if you contribute a small amount of hashing power to a pool and then take a proportionate share, you can get a fraction of a block's reward, but get a fraction of a block's reward every week, rather than getting one block a year, or maybe not. Alex asks, if I am a miner and I resolve a block and subsequently earn 12.5 Bitcoin, who is paying me that amount, and where do those Bitcoins come from? Very good. Also related to this issue, I read that when a block is solved, the successful miner gets the transaction fees on the block. But which transaction fees if it is a new block? So Alex, one thing that will probably help you understand both of these questions, or the answers to these questions, is to understand where the block comes from. If I'm a miner and I'm participating in in mining, I'm listing on the network. The moment I hear that somebody has found the block, that means that the competition has started again. A new round of the competition has started again. So at that point, each miner makes their own block. This is really important to understand. Each miner constructs a new block, a candidate block, one that is not yet valid because it hasn't got a valid nonce and a valid hash yet. But they construct a new block. And the way they do this candidate block is essentially they take an empty block and they take transactions from the mempool that have not been confirmed, and they fill the block. And they scoop transactions into the block, fill up the block. And as they do so, they choose which transactions they're going to pick from the mempool to maximize their profit. They validate all of the transactions to make sure they're correct, because that's their main function. They validate the block parameters of the block they created. So the transactions that other people have been sending over the last 10 minutes, the ones that weren't in the previous blocks, that haven't been confirmed yet, the leftover transactions that are for putting in a new block, these have fees on them. And as the miner fills up the block, those are the fees that they're going to collect. How do they collect those fees? And how do they collect the 12.5 Bitcoin? This is where it gets interesting. The very first transaction in the block is a special transaction called the Coinbase transaction. And the miner creates a special Coinbase transaction for themselves in their own candidate block. So they write a transaction at the top of the block, the first transaction that says, pay to Andreas miner address 12.6215 Bitcoin. And of that, 12.5 Bitcoin was the reward. And 0.115, the remainder, is the sum of all of the fees of all of the transactions I've put in. So how did I create that transaction? I took all of the fees, I added them up, I added that to 12.5 Bitcoin, and I've written a transaction, almost writing a check to myself. And that check is from nothing. It's from the Coinbase. There is no inputs in a Coinbase transaction. Basically, the 12.5 Bitcoin is created from nothing and is part of the reward. And the fees are basically the difference in inputs and outputs in the transactions, the leftovers from all of the transactions. And so I write that check to me. Okay, so I've written a check to myself, and I've put it in a block that I've constructed. It doesn't matter. That block isn't real. If I mine it and I find a solution, and I tell everybody about that solution, and they take that block and they accept it, and they put it in their copy of the blockchain, and they start mining on top of it, and it's embedded in the blockchain, then the check that I wrote to myself at the top, 100 blocks later, that check can be cashed. And I can then cash the 12.6 Bitcoin that was the sum of the reward and the fees that I wrote to myself. But it only becomes real if my block wins. So I'm writing a check, but I can't actually cash that check unless the block that I put it in is real. So where does the Bitcoin come from? It comes from the block itself, from the first special transaction, which is called the Coinbase transaction. The reward comes from nowhere. There are no inputs in a Coinbase transaction. It is completely newly created Bitcoin. The fees come from all of the transactions that got included in that block that the miner selected. And this transaction was written by the miner themselves. Which brings another interesting question. Why do they write 12.5? Why not give themselves 1,000 Bitcoin reward in that check? And the reason is simple. That transaction gets validated just like every other transaction, and every other miner, when they look at the block, will validate it and say, is that reward the correct reward for the current block? And if it's more than 12.5, everybody will reject that. So all of the mining that the miner did will be worthless, will be thrown away because they wrote the wrong amount in the check they wrote themselves. They can write less than 12.5 Bitcoin, which is surprising. You can actually give yourself less than the total reward. And if you do so, what you're doing is you're reducing the total number of Bitcoin that will ever be in circulation. But you can't give yourself more. Lex asks, is it possible to leave a transaction in the mempool long term? Yes, transactions don't expire. There's no such thing as a transaction expiry date. A transaction will stay in the mempool. Various nodes may choose to discard transactions from a mempool, but generally they stay in there. And you can retransmit a transaction again to reintroduce it into the mempool if, for whatever reason, it didn't propagate far enough and it didn't get into the mempool. Moina asks, if you were to look at the blockchain structure of a Bitcoin created in 2009 that had not been traded at all, and the blockchain structure of a Bitcoin newly created in September 2016, would they look the same or would they differ? And if so, how? That's a great question. There are, mostly they would look the same. Mostly they would look the same. There are some small differences. Keep in mind that every Bitcoin node will have to validate both the Bitcoin created in 2009 and the Bitcoin created in 2016. When you start a new Bitcoin node, then you build the blockchain from the Genesis block until today. your node will validate every single transaction in that, and has to have the code necessary to validate all of the transactions. And it has to be ready. If somebody submits a transaction and says, I'm going to spend this Bitcoin from 2009, your Bitcoin node has to be able to do that. So there are, however, some subtle changes. And these are improvements and modifications that have been introduced since 2009. For example, the block version number, which is part of the block header, is changed. It has slightly changed since 2009. In 2009, blocks had a version 1. And today, most blocks are version 4, I believe. And increasingly, version numbers in blocks are binary fields used to vote for certain features. So the version number is different. The Coinbase transaction probably looks quite different in terms of what's included in it. And that has been modified based on a number of bips. But both are recognized equally by the network. The transaction sequence number is going to be different because that field has been modified by a number of improvement proposals and used differently since then. Some of the capabilities since then have been turned off. Some others have been turned on. The script inside the Bitcoin unit that tells you who and how can redeem that Bitcoin, that may have changed. The old script is still valid, but the new script may have features that an old system might not recognize. So in the vast majority of features, the Bitcoin unit, the unspent transaction output from 2009 looks very, very similar to one created today. But there are some subtle differences based on improvements and modifications to the protocol. Kieran asks, by definition, Bitcoin or digital currencies are decentralized. If governments and banks are planning to have their own digital currency, does this not defeat the very purpose of its existence and go against the basic definition of a digital currency? Yes, Kieran, you have managed to figure out something that a lot of central bankers seem unable to understand. If you build a digital currency, a cryptocurrency, a decentralized cryptocurrency, and you make it so that one organization controls it, then it's not really an open cryptocurrency anymore. It's a completely different thing. And you lose almost all of the benefits of an open cryptocurrency. You lose, in fact, all of the benefits for which Bitcoin is interesting and useful. Just like if you build an intranet that is closed and inside your company, you lose most of the benefits of building the internet. And that's really the fundamental difference there. And so governments and banks have a difficult choice to make. If they build a cryptocurrency and they make it completely open and completely decentralized, then they don't control it. And if they don't control it, why build a new one? Why not just use one of the ones that already exist that they don't control? On the other hand, if they close it and control it, then they lose many of the benefits of an open and decentralized cryptocurrency. It's no longer an open and decentralized cryptocurrency. And really, there's not too many reasons to use a blockchain, which is a fairly inefficient data structure, to build, say, a digital Canadian dollar or a digital US dollar. Because the US dollar and the Canadian dollar and most other national currencies, they're already digital. Only 8% of the money is in circulation as paper. The rest of it is held on computers and databases of the central bank and other banks. They're already digital currency. You're really talking simply about changing the database architecture. And that's not revolutionary. That's not very interesting, and it's not decentralized. Maybe you could make it a bit less centralized and gain some benefits from that. But the real benefits of these digital cryptocurrencies is that they are open, borderless, decentralized and not controlled by anyone. So if you make them closed, border, full, centralized, and controlled by one or more entities much more closely, then you've lost all of the point of these devices. Great. I think that covers all of the questions we had in the forums. Once again, pardon me. Thank you so much for participating in this massive open online course. Not quite massive, but our open online course for the master's degree in digital currencies for the University of Nicosia. I've been your host, Andreas Antonopoulos. Always a pleasure. We have one more session next week, and the materials will be released today. Please don't forget to ask questions on the forums in advance, not just so that we have questions that we are ready to answer, but also so that you can collaborate with the other participants in the program and try to answer each other's questions and see each other's questions so you can learn. Thank you so much for participating, and see you next week.